Okay, here we go. So we got limited time, so we gotta get rolling. Okay, so a little calculus Jeopardy here. I want to just review what we did yesterday. Okay, so here's the question. Okay, now I didn't really want to do it that way. I don't think, did I? Okay, derivative is, hang on, I messed that up already. My goodness. I'm not on a roll today, anyway.
No. Yeah, I don't know.
There.
No,
we can't have that.
what was underneath it?
Oh, it doesn't matter.
No.
Wasn't supposed to be there.
Plus C.
Okay, so the little calculus Jeopardy. The answer is the derivative is 3x squared. And then I don't really need this guy, do I? So I can just...
So it's x to the third. The antiderivative is
The
x to
answer
the
is
third.
X.
Okay, so what's the answer?
X cubed.
So the answer is what is, in the form of a question, what is the function?
What is x cubed?
X cubed, right? Okay. Now,
Thomas Voss?
let me give you a little, we got some terminology that's very specific here. Okay, Shane, put that away, whatever it is. Something was attracting you. Okay. We could also have said this, couldn't we? Did I get this mixed up? No, I guess I didn't. I think I hurried it together.
10 to the 798.
So you don't need any of the C's, though.
Okay, so what I really wanted was this. Okay, I did this backwards. I got this all mixed up.
Yeah, this isn't
Why
very
is it plus
organized.
11?
Because it's a constant.
Oh my gosh, I got this all messed up. Okay, now here's what I meant to do.
Arbitrary.
I was cutting and pasting, and I got confused evidently. So the answer is, what is the function x cubed? Now that is what we would say, that is an answer, but it's not necessarily the answer. It's an answer. It's a specific answer.
It could be x
right?
cubed plus 1, x cubed plus 2.
Okay, so f of x equals x cubed is an antiderivative of this. But it's the general form would be x cubed plus c. Okay, so we could have x cubed plus 11 or x cubed plus 11. Or x cubed 3x squared. What is the function? Oh my gosh, I got this so mixed up. This is supposed to be, all this is supposed to be x cubed plus 11, or an example would be x cubed plus some huge number, 10 to the 798, or whatever. Doesn't matter. Generally speaking, it should be this, x cubed plus c. That's our general solution. Now, what I want you to...
No, wait, but I thought that was the question.
That was a lot of writing
Yeah,
to do
you said
nothing.
that's the-
Yeah.
No, but that's the question. You mean the antiderivative is
This
x
whole
cubed?
Jeopardy thing.
Okay,
Throwing us off.
Can we skip this page? We've got this.
So we could say that, this is an example, but we got to put that plus c on there, because when we differentiate, because we're playing Jeopardy, forget about the question answer stuff. The antiderivative needs to include the c, because when we differentiate, we kind of said this yesterday,
Yeah, we said it several times.
when we differentiate, that c is going to go away, so we have to account for it.
Right.
Okay, now what's a better way to look at this is that g of x represents an infinite number of solutions, each of which has a meaning. Let's look at this in a little different context. Let's solve a differential equation here. Okay? Now, a differential equation, all that is, that's just an equation involving derivatives. So we've got a derivative right there, right? It's y prime. So the solution of a differential equation undoes the derivative and gives us back the original function. We would have to differentiate to get that, right? So playing calculus Jeopardy, for now, that's the only game we know, we can turn this thing around, right? The answer is y prime equals 2 if the question is, what is the function? Y equals 2x, right? Plus c. That's what we'd have to differentiate to get 2 for an answer. Agreed?
Yes.
Okay. So then, what we want to see is that's a general solution where each of the infinite values of C represents one distinct different answer. Together, if we take all those together, we call that a family of curves, because they all have the same look, but they're going to differ only by, we're going to differentiate them or distinguish them only by the value of that
C.
constant, right? The constant in this case, now we can see that this family of curves represents all the lines with slope 2, right? We could change the y-intercept as we please, but all of those lines are carbon copies of one another. The only difference is they've just been shifted vertically, right? C is going to change. Okay, so if we want to look then, well, okay, that's it for that page. Okay, so that's a general solution. Now, what if we want to do a little more specific thing? What if we want to do the same problem, only this time we're going to pin down the answer. We're going to say, we're going to solve the same differential equation, but this time we know that the curve has to pass through a fixed point at 0, 2, right? And so we did something like that yesterday too. We can... Oh, okay. There's nothing there to get rid of. Okay, do I have anything else on that page? I'm fooling myself. Okay. Here's where I want to do this. I want to graph those things, right? So let's see what this looks like. We just get a little sample of what a family of curves looks like.
You can visualize it.
Yeah.
Good luck.
Okay, so let's look at this then. What if we've got... We said that the answer was y equals x squared plus c, right?
Yeah. Doctor, I have a question for you.
Okay, hold on one sec.
Do you just make this class up on the fly, or do you actually do any planning?
I mean, a little both.
Okay. So today's one of those ones that
Well, kind of.
semi-planned it out.
Yeah, it didn't work so well. But. Okay, so we had the answer for this, right? We said that y equals 2x plus c, right? So let's look at some examples then. If I plug in...
Maybe we can all visualize this.
Just see.
So there's y equals 2x plus 3. That's when c equals 3.
Yeah.
Here's an example where...
0. Not 0. Just 2x.
2x plus 0, right there, right?
Well,
If we start to add up a whole bunch of these, you get an idea. And you know what it is.
like a zebra.
Hey, can you guys not talk back there, please? Thank you. There's 2x minus 3. So we're just going to get, when we stack these things up, we get this family of curves. Now, we wanted to pick the one out that went through the point 0, 2, right? Okay, so that's going to be this guy.
That crosses the point of origin.
Right, that's going to be 2. There's the one we're looking for, because it's the one that goes through the point 0, 2. So that's the one. If we want to figure out what that is analytically, we just have to solve for C. Right?
So we know how to do that.
And you guys know how to do that.
Yeah,
We
we
just
can do
plug
that.
in the values and go from there. Okay, good. Okay, so
This thing's a little
So here's something. Yeah, here's something a little bit new. Now we're going to get into some more of the theories, get a little more conceptual. So you got to really think about this hard. So if we start off with a derivative like this, now this is pretty cool. Watch the magical graphics at work here.
All this is cool.
So this is the normal form of a derivative, right? dy dx equals f prime of x, I should say. Let's ignore that little faux pas, please. So dy dx equals f prime of x. If I want to put that into differential form, I can just do this. Right? I can just drag this guy over here. Let's get rid of this. We don't need that anymore. Put him right there. And now all of a sudden, voila, we got it in differential form. How about that? Yeah.
That's
Yeah,
pretty
how about that? Pretty impressive, huh? Okay, so we put this in differential form where it's set equal to dy. Okay, now what that does for us is it allows us to solve for y. Because I want you to think about what an antiderivative does, right? It undoes a derivative, right? So if I were to anti-differentiate both sides, and our symbol for that, remember, is that.
Isn't that black thing that?
It's the red. It's this symbol. That
And you put
means
the SS up there.
that symbol, that integration sign. That means
Yeah, but that black
Is the
symbol.
black-
Yeah.
the black thing is supposed to be a
No,
Y.
down.
Yeah, he's
That's it.
referring.
Oh, right
yeah,
there,
yeah,
yeah.
yeah.
That's what I'm. Yeah.
That's it. Right. That's it. Perfect. Okay. So then, the antiderivative of the derivative of y. Well, those cancel. That goes away, and that goes away, and we just get the y. Right.
Yep.
And so there's our result. Right. Only that's supposed to have a prime in it. Okay? And so the original function is f of x, and then we say that we're going to label this capital F of x. That's the antiderivative function. Okay, now they're related. They're related. We already know this relationship in the other direction. If we took something like, for example, if I took f of x equals x squared, and g of x equals 2x plus c, those two functions are related, right? This one we could say, if I go in this direction, I would say that g of x is the derivative of f of x, right?
And f of x is the antiderivative of g of x.
Right, exactly. But f of x is the
Yeah.
anti.
Yeah.
Does that make sense?
Yeah, it does.
G of x is the antiderivative.
No, G of X
No.
is the derivative.
G of x is the. Oh, hang on.
Oh yeah.
Hang on. Sorry. It's messed up. That's the derivative, right? Sorry. That's the derivative.
Yeah, there you go.
Okay. If I differentiate x squared, I get 2x. That's the derivative. Now, if I flip the arrow around, so I go like this, and I go in the other direction, that just means it's, instead of it being a derivative, a function and derivative relationship, now it's a function antiderivative relationship. I got to add the plus c there now, right?
Yeah.
Make sense?
Yeah, it does.
So then we've got this inverse relationship set up here. Okay, we know that derivatives and antiderivatives undo each other. So we should expect then that if I've got this integral to begin with, this antiderivative we're calling it. Soon we're going to call it an integral. Remember what this means. We've got the integral symbol in the dx, and there's the integrand inside. That's the function we're playing calculus Jeopardy with, right? If I anti-differentiate that, it undoes the derivative, right? And it reverses the process we've been doing all year. That's what we've done so far, right? Does that make sense?
Yes.
Okay, so then differentiating that makes those two functions equivalent. See,
It's undoing the anti.
it's undoing the antiderivative, right? By the same token, I ought to be able to anti-differentiate a derivative.
Can you anti-differentiate the antiderivative to make it regular derivative?
No, it doesn't work that way.
No.
And then
Yeah, we're
That
just
was
inverse
brewing
inverse.
for like a minute and they got shot down real quick.
So then we could do the instead of having the derivative on the outside, we could just flip that around, right? And they're still inverses, and so they still should undo each other, and they do. The antiderivative of the derivative of a function leaves you with the bare function, right? Okay, so these are important theorems in calculus. All they really mean for us, though, is calculus Jeopardy. That's it.
Yeah.
When we're in
That's
college-
really-
oh,
that's
yeah,
really what
calculus
those
Jeopardy
represent.
right there.
All right. Now, let's try a couple real
Wild
quick.
card.
No, not quite. It's the secret. Okay, let's try. How about? Okay, so. Okay, one thing I remember one thing I wanted to do here is I want to give you a better recipe for going from a derivative formula to an antiderivative formula. So let's just take for example a trig function.
You
What
should
if
teach
we
us
do-
the best way, and then I would stick with that one.
I'm going back to real quick.
Good luck.
Thank you.
Okay, what is that? Okay.
Isn't it negative cosine? Or is it cosine?
No, cosine times, it's a chain rule problem, right? If I've got the derivative of sine with respect to x of sine u, I've got the derivative of sine something is cosine something times
What are you talking about?
u prime, or
Oh.
d of x.
Good.
Right? Okay, now here's how we can turn this into an antiderivative formula. Okay, Shane, put that away.
And
Seriously.
It was, she's trying to make me read stuff.
Yeah, Caleb, put that away. Put that away. So if I want to turn this into an antiderivative, I'm going to put it into differential form. And this is leading us to something important. This is leading us to how we solve a separable differential equation, which is big time stuff. We're getting too soon. So this is good preview of what's to come. You have to know this. If I multiply both sides through by dx, remember that's just how we put it in differential form. We're getting rid of the dx on the bottom, right? And so we're left with the differential form of the derivative of sine u equals whatever's over here. Well, look what happens. Dx on the top and dx on the bottom cancels. And I just get cosine of u du, right? Okay, now if I want to turn this around and write this as an antiderivative function, then I want to undo the derivative, right? I'm going to reverse this process. Got to treat both sides equally. So I'm going to do that, right? Taking the antiderivative of a derivative does what? Cancels them. So those go away, right? And I end up getting, on this side, I'm going to get sine u, and I've got to have a plus c there. I'm going to call it c1. And on this side, I've got the antiderivative of cosine u du. Now we just turn that around and that's our formula, isn't it?
Yeah.
Right? So now we've got the integral, or the antiderivative of cosine u du equals sine u plus c. We don't need the c1, we'll call it c. Thought we needed. Yeah. Okay? We can do that for any of them. All we do is we just multiply both sides by dx, integrate both sides, or differentiate both sides. I'm just going to add a c to this side, and then that's it. So all of those derivative formulas yield antiderivative formulas, standard forms. Okay, now let's practice one of those. What if I gave you this problem? What if I wanted you to find this antiderivative? Whoops. No, I'm not where you're supposed to.
Why? Why are you going to do that?
Okay.
It's square root. We don't need that.
Okay, what are you supposed to do with that? Good question. Now, keep in mind that the antiderivative is just a derivative in reverse, right? And when we did derivatives, now think about what the process was when we did a derivative, like say
yeah,
this.
that took you a long time.
What's our answer to that one?
The antiderivative of this?
No, just derivatives. This is old stuff. We've been doing forever.
Yeah, 2x plus 3.
Right?
Wait, what's that in correlation to the one that we
Okay,
just had?
watch. Now watch. Here's how that correlates, why that's important relative to what we're doing now. This is differentiation.
Yes, it is.
Okay, that's
But if we do that backwards, it's anti-differentiation.
yeah, this is taking an antiderivative. Notice that they still are, there's still a term-for-term correlation here, right? The blue term goes with the blue term, the red term goes with the red term. Either way you go, right? Make sense?
Yes.
So therefore, now this is sort of a conceptual argument, but this is airtight here. You see if you agree with me. If I turn this around then, just like I had the huge benefit of being able to differentiate term by term, when I had a sum of a bunch of terms, I could break it up into separate, simple, small derivatives, right? Separate, or I could break it up into separate pieces. Because there's a one-to-one correlation between the terms in the derivative and the terms in the answer, when I anti-differentiate, I can do the same thing, right? So going back to our problem, what's one thing I definitely want to do here?
Square roots out of there.
Okay, I want to get rid of the square roots, but that plus sign is not problematic for us because I can break it into separate pieces, right?
Yeah, we're not worried about that.
Okay, so first things first. We've got the square root of x is just an x to the 1/2, right? Plus 1
over
1/2 x to the minus 1/2, right?
correct.
Okay, and then
Yes.
dx. And I can split those if in my mind at least, I'm splitting those into separate antiderivatives.
Right.
So let's just follow our rules then. What is our power rule? Remind us from yesterday. What's our power rule for antiderivatives? The antiderivative of u to the n du is what? How do I play calculus Jeopardy with?
N minus 1. Or plus 1.
No.
That's what I meant.
U to the n plus 1.
Over D.
Okay, but now almost.
There's
Now,
a K.
think about, well, we don't need the k's this time. The k's were just to kind of build this general formula. But if I were to differentiate this, I've got to get this result, right? The integrand is the answer when I differentiate. So if I differentiate this problem, I'm going to get quantity n plus 1 times u to the n. That's not what I have there. Yeah, I don't have the n plus 1 constant out front, do I?
What is that U2?
N?
Oh, I didn't distinguish that. I didn't know what it was.
It's an n. Okay.
It looks like
Is that a bird?
19 or
Okay, so then because I don't have the n plus 1 out front, it must be divided away, right? So I need an n plus 1 on the bottom. So there's our formula, right?
Why wouldn't?
Because, makes sense? Okay. Because now this works. When I differentiate this, the c goes away. When I pull the n plus 1 out front, I've just got n plus 1 divided by n plus 1, so they cancel. Times u to the n minus 1. Well, that's my answer. That's perfect. It works. So that's the formula, right? Let's apply that to both of these two terms. So in the first term, what's n?
Yeah.
1/2. So then the answer must be x to the
1.5
okay, otherwise known as 3/2.
over 4.5.
No,
Why?
divided by 3/2, but I don't want to divide by 3/2. Instead, I'll multiply by.
So exactly what I said in a different way. Divided by 1.5.
So 2/3 x to the 3/2 plus. What about this guy? What is it? X to the 1/2. Okay. And divided by 1/2, which is just times 2, right? But I got that 1/2 out front already. So it really is just x to the 1/2, isn't it? Right? Because when I differentiate, that's going to punch that 1/2 out front as a coefficient, which is what I have. Okay, so. Oops. And then I just need my plus c. Make sense?
Yeah.
Okay. All right. How about that. Okay, want to probably get rid of the square root, sure. Okay, but now when you're doing antiderivatives, the mindset you got to get in is you've got this list of antiderivatives which you need. Everybody have your books? No. Here, let me just print this out for you. So you got to have this. You got to be looking at this. This is the only playbook you have.